Well, hello, hello, good morning. I hope you all had a good insights of the keynote session. Speaker for today's session is Holly Smith. She's our Senior Resident Solution Architect. She'll be talking about Photon and Spark today. The session is like around 30 to 40 minutes, so I'm not sure how much time we would get for questions, but we would definitely be like finding time outside, or she can be sharing FAQs with you to get more insights. But let's welcome Holly Smith here.
All right, good morning, San Francisco. Yeah, all right, I give it an 8 out of 10, well done. So my name is Holly Smith, and I work for Databricks. Now, one of the best things about working for Databricks is that they hire the smartest people to solve really hard problems. But this introduces a new problem, and that is when these smart people assume that everyone is just as smart as they are. And this makes learning about new topics really hard. And I'll give you an example. When I joined Databricks, I had no idea what Spark was, and miraculously, I passed the interview by super-duper promising that I'd learn what it is. And aside from learning the syntax, I would come across phrases like, Spark runs on JVMs. And so I'd say, OK, what's a JVM? And I'd get the answer, it stands for Java Virtual Machine. And I'd say, OK, but what is a Java Virtual Machine? And the response I would get is, don't be silly, you know what this is. They're those things that Spark runs on. And this sort of thing would happen time and time again. So when Databricks bought out Photon, I saw this phenomenon coming a mile away. I could see a lot of people nodding along, pretending to understand what it was. But when you scratch the surface, the facade fell, and they painfully confessed that they didn't get it at all. So who better to take you through what Photon actually is than me, Holly Smith, Chief Dummy? So what qualifies me as Chief Dummy? So first of all, I don't have a CS degree. I never thought I'd be in the position where I was ashamed of my maths degree, but here we are. I'm also not like a Spark contributor. I did manage to pass my Spark exams. I wouldn't consider myself an expert. But despite this, I do have a few things going for me. Firstly, I can read. Thank you. Not only did I go through the Photon white paper, I went through nearly every paper that the Photon paper referenced, and even then some of the references that those references had. And apparently I have a lot of spare time on my hands too. Secondly, working at Databricks, I can annoy the hell out of people who understand it a lot better. We've got an SME group. I can even bother the engineering team as well. And finally, I have no shame. I can ask the dumbest questions and just keep on going. So come with me on this journey as we dive into what Photon actually is. Now, to understand Photon, you really need to understand the fundamentals of Spark and the challenges with it before diving into some real-life practicalities. By the way, this section goes from 0 to 100 real fast, so bear with me. And to benchmark how advanced something is, we will be using the industry standard, the Nando Spicy chart. From the looks of things, we've got a range of abilities in the audience. I spot some SMEs in here. There is a guy in the suit at the back who looks like he got lost on the way to the exec forum. Don't worry. No one's going to blame you if you can't manage an extra hot, spicy Nando's, because frankly, I can't either. I was going to randomly pick a name to go from the white paper to go next to extra hot, but then someone from comms pointed out that could be construed as harassment, but probably a bold career move. Although I realize I've now put all the founders there instead. No one tell anyone. All right, so let's get back to some seriousness. So let's start easing you in with an extra mild, why is Spark needed? So data is growing and is possibly true more now than when Spark was created back in 2015. This growing data is also ugly. We are not starting with some nice and neat data in a warehouse. It's in a variety of file formats. The column types are all over the place. It might even be 90% null, and it's probably coming at you fast. So we could just keep throwing like a bigger and bigger single machine at it, but one, the odds that you're using it at 100% capacity are pretty slim, meaning you're probably wasting a lot of money. When you're doing things with big data, it benefits from running things in parallel, which you can't do with a single machine. And if that machine dies, you've had it query progress over. So to address this, we are going to group smaller machines together and attack it from that angle. But when you think about it, when you're working across multiple machines, you don't want to have to manually decide what sort of data goes where. You just want to be able to write your code to say what you want to do, not how to do it. Speaking of joins, this is not the only thing that you're going to want to do with your data. People are going to want to do complex data processing, things like advanced statistics. Apparently LLMs are a hot thing people want to do these days. And having something that is open source is something that anyone can contribute back to. So so in our group of machines, we're going to allocate one of them as the driver and the rest as workers. The driver's role is to take instructions from the user, pass them, and then figure out the logic of what worker should do work. The worker's role is to take those instructions, do the work, and either report back a success or, in some instances, a failure. And this is where the driver is quite clever. It can help redistribute work if one of the workers fails. Maybe you've got a dud machine, maybe you wrote some really terrible code, no judgment here. And this is called fault tolerance. So what does this look like when you start running your pipeline? One of the first things that's going to happen is your data is going to be split into shuffle partitions across the workers. This diagram shows one shuffle partition per worker, but realistically, you're going to have many more. And the word shuffle is going to come up a few times. Why do we call it that? Because it is shuffled between these workers. If I have a table of Nando sales and I want to find the average spiciness per country, I'm going to have to shuffle all that data between those workers. So let's zoom in at how Spark breaks down data processing. Spark has a hierarchy of how it breaks down this work. It has actions, which break down to jobs, and then to stages, and then to tasks. And what each specific level does is a bit of a faff to explain. But the main takeaway is that we've got multiple levels for optimization, multiple levels of parallelism, and increasing granularity. Where at the final level, we have a task that's processing a single amount of tiny data, partition of data. Now, this is great and all, but how on earth does Spark decide what data goes where and what to do? It uses something called the Catalyst Optimiser. So let's go another layer deeper and have a look at this in detail. The Catalyst Optimiser does four main things. So it's going to start by taking our input on our code and our data. It's going to analyze the logic that you coded. It then optimizes this logic using some rules, and it then makes some physical plans with the data we have, literally saying what data should go where. Once we have the physical plans we want, we then go into code generation. And this last step is important. It takes all of our rules, all of our optimizations, it does some trial and error, and then it turns it into code to execute. Got it? Good, because let's go one level deeper. So to start with, we've got our code that we are submitting. We also have our data that is represented in a data frame. Spark has its own version of a data frame. It's ultimately a collection of rows that have structure, and they've got metadata. We then make a plan without doing any fact-checking whatsoever, and this is an unresolved logical plan. Using the data frame we have to hand, the data available in the metastore, we then start checking whether it makes sense. Do we have the right columns? Have you specified the right options to make this work? Once we've sense-checked it, we then optimize it. Stuff like, if you're doing a filter that only keeps 10% of your data, at what point can you discard the remaining 90% so it isn't going to waste? If we're doing some joins or some aggregations, we'll test out multiple ways to do it and then pick the best one. Once we're happy with the plan, we then have to turn that into code. And to do that, we're going to generate loads of code, loop over it until we have the best version. And then bam, turn it into RDDs, and that's what the code is going to run on. And this last part is fundamental to the intricacies of Photon, so let's go one level deeper. How does code generation really work? So picking up from the green boxes, we have our physical plan, and this contains information about any filters that we might want to push down. It'll also pick the right join strategy for us as well. Now, if you're sat here thinking, how hard can it be to do a join? I'm here to tell you that that simple syntax is deceptive. There is a lot of wizardry that is going on underneath here around picking the partitions, maybe some duplicating of some data, and also looping over it too. So we have our physical plan, and then Spark starts to do some pattern matching. Oh, this looks like this kind of looks like this, we'll give it a go. And these patterns form wider combinations or trees. And Spark's going to start recursively testing these combinations to see what matches to give a stable result, and then turn this code into Scala. But I think the person who coined the phrase tree here needs to go outside more, because trees look like this and not like this. And these combinations can get enormous and unruly, especially when you've got very wide tables. They're overly interconnected and a nightmare to unpick. And this has a term that was coined by someone who clearly had been outside. This is known as a code volcano, which is nice and dramatic. It's the right shape, and it's got that, certain sense of fear of existential dread in it. So the metaphor checks out. So Scala is going to then convert this into Java bytecode. And this Scala stuff has some important implications for us, so I will come back to it later. But that's the code side of the story. We need to interact with the data too. The last step is to turn all of this into RDDs, which stand for Resilient Distributed Data Sets. Resilient because they are fault tolerant, distributed because it's across our workers, and data set because it's data. And it's worth noting at this point that data frames and RDDs are largely row-oriented. This means when we start chopping up the data smaller and smaller, we're going to keep lots of different columns together. So back to that point about language, and as it's so important, it's time for a history lesson. We start with C++, which was created in 1979. Oh, I have realized the formats have changed a little bit. My timelines are a bit off. It's fine. But this C++ compiles directly to machine code, to the hardware. So this is like the chip, the operating system setup that we have, literally saying what part of memory holds what data. So what is hardware? Like, we all know it's ones and zeros, but how does that make stuff work? This is grossly oversimplified, but it will serve for our purposes. We can represent numbers in binary, so 5 is 0, 1, 0, 1. That's no 8s and a 4, and no 2s and a 1. We have to define how long it is, or how much memory it takes up. Otherwise, where does one number end and the next one begin? We then have to put it somewhere, and this is called an address. And you can interact with these things directly in the C++ programming language, making sure that these spaces, this memory, is either empty or OK to overwrite is all part of memory management. So what about letters? In the same way that we decided a 1 here actually means 4, why not just have a mapping that is 8 ones and zeros corresponding to a letter? 0, 1, 1, 0, 0, the top one represents a lowercase a, and this series of 8 ones and zeros gives us combinations for 128 characters. And this mapping is known as ASCII encoding, where the A stands for American. So if your Nando's order is chicken wings, well, that's all fine. All those letters are included in the 128. But if you go to the UAE for the same order, we're going to need a whole new system, and it's going to take up a whole lot more space. This is relevant, I swear. It's not a massive tangent. Right, we'll come back to it later. So back to languages. So C++ is blazingly fast. It is based off the original C language created in 1972, but that was so basic it didn't even have things like strings, and it did nothing to help you manage your memory when it got too full. One of the big drawbacks of this family of this language is that you also have to have intricate knowledge of how your memory is arranged and how to interact with it. This isn't so much of a problem in the 70s when you might be building something super specialized, but it makes it a nightmare to generalize. Completely separately to this, we have Java, created in 1991 and released in 1995. And so instead of resolving to machine code like C or C++, it compiles to bytecode that can run on any platform on operating system. And this is made possible with something called the Java Virtual Machine, the JVM. This abstracts all that hardware interpretation, meaning that you can write your code once and it will do all that difficult hardware interpretation for you. And this is what a Java virtual machine is. It is not, as I originally thought, a type of flavor of virtual machine from Azure of type Java. Not only is that wrong, it is very wrong, and I don't know why I'm telling a room full of people this. So Java comes with a lot of features that it's led to its popularity, but importantly to us, it's got better memory management, and it allocates dedicated space for us to chop and change what we're storing, but it also clears up data that we're not using anymore or is too fragmented to use sensibly. And this is known as garbage collection. It runs automatically in the background and can even detect when memory is getting full, meaning that our programs are less likely to fail. If you've ever come across the phrase heap before, on heap is the area of memory that the JVM manages, and off heap, well, that's down to you. Garbage collection can't save you there. But as prolific as Java is, there are some shortcomings. But there are some big challenges that data people care about, like managing concurrency to make something both efficient and, importantly, correct. Enter Scala. Scala runs on the Java platform, meaning that it runs on that Java virtual machine. And though originally released in 2004, by 2011 it had some commercial backing, meaning that by 2014, when Spark was created, it was in its heyday. Scala is more concise than Java. It allows for functional programming. You've got built-in support for concurrency and parallelism, but it still uses that JVM to benefit from things like memory management, which is particularly pertinent when dealing with data-heavy programs. Writing data to memory is faster than writing to disk. Oops. Which is our long-term storage. And writing to memory makes it ideal for temporarily storing kind of intermediary results of our data processing. But if you start overfilling it, though, there are a few consequences. You spill over from that fast memory storage and then end up using the slower disk storage. And this is why spill to disk is a critical Spark metric. The second thing is you spend more time on garbage collection processes than actually processing your data. And again, this is another key metric that we monitor. Or my favorite, you end up evicting something from memory that you or a coworker actually needed later. So to summarize, the C family allows you to write blazingly fast code, and the Java family has more functionality. Now, in the same way that I struggled to understand JVMs, something else I really struggled to understand was the term vectorization. And apparently animations in PowerPoint too. Right, vectors. In my head, a vector is one of these thingies that looks like that. And that's it. But it turns out there are different types of vectorization, and people interpret it in slightly different ways. And so the first thing to mess me up was SIMD, which stands for Single Instruction, Multiple Data. And it kept being referred to as vectorized. And originally, I thought that this was what made Photon a vectorized query engine. But then I thought, hang on a minute, we've been talking about SIMD for ages. Turns out this was introduced back into Spark in 2020. Sorry, Reynolds. So how does SIMD work? It's basically a better integration with the hardware. Without SIMD, it's single instruction, single data. So let's say we have two sets of values we want to add together. Without SIMD, we take our pairs of numbers one at a time, and we do it and we do one, and then the next, and then the next. But with SIMD, you can do multiple sets at a time, and we can pass it these vectors. And this gives us the benefit of memory parallelism. And if this looks like it is really oversimplified, it's because it is. In reality, this is not trivial. You have to have the right kind of hardware, you've got to have the right kind of know-how to get it to work, and even then, you can't get 100% coverage on all query types. The next one to trip me up was vectorized UDFs, i.e. user-defined functions. This is custom logic that is not covered in Spark. This might be some niche algorithm that only you are using. Vectorized UDFs use Apache Arrow to better organize the layout of your data in memory and reduce the amount that's being moved around. One of the key features is that it works in a batch level instead of row at a time. And this batch is what makes it vectorized. These were introduced to Spark back in 2017, and it was at this point in my research I realized I had really been asleep at the wheel. So when we're looking at vectorization in general, we can see a few trends. By the way, I couldn't find out what the opposite of like not vectorized was, so we're just going to call it not vectorized. We're all in agreement? Good, I see some nods. Thank you. Thanks for playing along. So what is vectorized? It is batches of data. It is not just one record at a time. These batches are batches of column data. And this data is all of the same type. There is no mixing and matching. And now, whilst I've spent the last 20 minutes talking about the technical details of Spark, it is important to recognize where Spark fits into the ecosystem. It is ubiquitous. It is an essential skill for any data engineer. It is downloaded millions of times a month, and it powers all sorts of data programs. Its flexibility allows it to handle multiple different types of data. If you've got multi-language support, you can do streaming, you can do batch, which makes it ideal for any lake or lakehouse implementation. And it runs on many platforms. Databricks, of course, being the best, in my opinion. Other platforms are available. And it is worth noting that the Databricks version of Spark has a lot of additional features compared to the open source one. So if it's so popular, that means it's perfect, right? Well, sadly, not quite. Data landscapes change, and people always want to lower the cost of their processing through efficiency. And since its inception nearly 10 years ago, there has been a relentless drive to improve performance. And whilst there's been a good run, they're kind of running out of things to optimize. So we've squeezed a lot out of the hardware. Earlier, we spoke about SIMD, which to get working is really hard. You absolutely have to know what you're doing for that. There's also caching strategies. This is around storing your intermediate results in memory for later use. The optimization comes from choosing what to cache, what to evict, and how to balance it across workers. To improve Catalyst Optimiser, I keep saying we. I didn't do any of this. We started parsing more statistics to make better decisions. Things like feeding back statistics once you start running your job so that you can better partition your data with more accurate metrics. This is known as adaptive query execution. The second thing was having better metadata stored with our data on disk, and this came in with Delta. Speaking of Delta, which we're of course all using for our storage layer, that allowed us to better optimize the size of the files, improve the layout of our data, and put this data that was similar together to make it faster to scan. The speedups over the years have been impressive. This is by no means an exhaustive list. But it was getting to the point of diminishing returns, and some less than ideal areas were coming into sharp focus. We're stuck with a couple of design choices. Trying to overcome performance issues created by the JVM required so much in-depth knowledge. Remember, there's a lot that goes into that JVM to make it work on any machine, still do garbage collection, and then you want to start kind of like fiddling around with the internals. This is incredibly tricky to do. The second thing that we're left with is our row-based setup that we have. Our RDDs and our data frames are still largely row-based. And this sucks because a lot of good stuff out there is columnar, not just things like SIMD, but all the decent file formats are columnar too. And finally, code generation can be a nightmare to debug. I'm not just talking about when some unskilled data engineer like yours truly writes some truly rubbish code. I mean when you're optimizing that code generation logic, you spend more time building custom telemetry than you do actually optimizing what is going on inside. So to recap, maybe you're a Nando's extra mild and this all went over your head. Here are the important points. Spark is ubiquitous. You will struggle to do data engineering without Spark skills. The lowest level of execution is called a task. Catalyst does a lot of the logical optimizations as well as generating code. That code executes in Scala, which is built on top of the Java virtual machine. JVMs are useful to help manage memory, but they can come with an overhead that is hard to optimize. And finally, fast is never fast enough. Just because we've got loads of performance improvement through Spark and Delta doesn't mean it's done. Enter Photon. Enter Photon. Thank you. And again, this goes into detail pretty quickly, but I will ease you in with a mild. The way I see it, there are 4 main categories of differences with Photon. Firstly, and I think you saw this one coming, we're going to rewrite some of that slower Scala into faster C++. And while we're at it, we are going to get rid of some of those messy trees. We'll take a look at the crux of what makes Photon a vectorized query engine. And if you combine these 3 things, you can start doing really clever things like code specialization. We've got some text examples and then some join examples too. So let's have a look at this new language. If the JVM used by Scala is so slow, why not switch language and not use it anymore to speed things up? We're not throwing everything in the bin. It is literally that last step. The code we create isn't going to be in Scala anymore. We're still going to do our logical planning. We still do our physical planning. But now we have the option to write our last step in C++. And this bit is key. It's only going to switch to C++ if it matches certain patterns. It might not happen 100% of the time. But because we still have to interact with original Spark, we've not fully escaped the JVM, and we still have to play nice with it using an interface called the Java Native Interface, the JNI. Some bits of our code can run in Spark, and some bits in Photon, and we can interchange between the two. By the way, if you've ever heard of a little feature called predictive I/O, it's taking that file scan and photonizing it to, among other things, remove one JNI exchange. But you can also see this where the exchange happens in the Spark UI. If you've never seen a Spark UI before, when you run some code, you get a nice diagram showing what's processed along with some statistics. These are the two most granular levels. You've got stages and you've got tasks. The stages are the big boxes and the tasks are the little ones. Now, our original plans would all be Spark Plan Blue, but now our Photon activities are going to be represented in yellow. And if we zoom in on our plan, we even have some nice text here calling out that it is a Photon stage. And we have to be careful here because our blue tasks are row-based, and in yellow, we're flipping them to be columnar. Now, that's OK to do once or twice, but we want to avoid flip-flopping between them because it's going to introduce loads of overhead. But this idea that we can chop and change is pretty clever. First of all, programmers can use exactly the same syntax as they would for Spark. No need to try and convince thousands of users to learn something new. No need to refactor. Just enable Photon for your cluster and wait for it to happen. Secondly, it fits really nicely into Catalyst, meaning that we're still going to benefit from all of our other previous optimizations like better statistics and AQE and delta. And finally, you don't need 100% coverage from day one. If it's not there, use the old-fashioned code generation to fall back on. This means you can have a gradual rollout. Start with the patterns that are seen the most, and then work down from there. And lastly, when someone does add some cool new feature to open source Spark, it's not like you have to instantly rewrite it to incorporate it. You can use it as it is. So let's turn our attention to code generation. So instead of faffing about and iterating over our trees, like, oh, what about this branch with this, or like maybe this, OK, now compile it. Instead, we are going to have lots of smaller pre-compiled code kernels ready to go. Just as a seed kernel contains the secrets to how plants are built, these Photon kernels contain the secrets to how Photon processes data. And because we've got rid of this wild and sometimes unpredictable code generation, we don't have to have this massive array of custom telemetry to unpick everything. Instead, we can just use normal metrics and use like normal software techniques like unit testing. And this cuts down on debugging time massively. We are talking weeks instead of literal months to unpick issues. And now we can be super specific with these kernels on how we match them to the data and how we can make things even faster. Now, some of you might be thinking, interpreted, didn't we have this back in Spark 1.6? And technically, yes, but it was a vectorized, so let's talk about vectors. And vectors, remember, are basically batches of data in a column. So instead of reading in rows of data in different types that look like this, we are now going to turn it around and make it look like this. Now, this might not be a massive revelation, but bear with me because it has some important features. Let's say we have this code here, which is just a basic count. How does Photon make this faster? Firstly, all of the values are stored next to each other in memory, and because it's all the same type, this is just integers, it is now way more compatible with modern file types like Parquet, and it's more compatible with SIMD and Apache Arrow. So we've got better use of the hardware. We wouldn't have been able to do this with our mishmash of columns and strings and dates. But not only are we going to do this, we can take it a step further to make it even more efficient. We're going to add on whether the value is a null or not. And so instead of scanning our integers to figure out if it's null or not, we just have this Boolean, this yes, no here to see if we can skip over it. But let's take this null idea one step further. And we're going to decide which of our data is relevant to our query and add on position list when it is. And if we had all null data, we could just simply have an empty position list. And we don't even have to scan our data anymore. We can just see this empty position list and know not to bother with this batch. And because we have this information about what's null and what's relevant, we can start to do clever and efficient things. All of this logic is contained within a kernel, so let's take a look at what a kernel looks like. If we wanted a kernel to find the square root of our values, step one, write it all in C++. And again, this is all in the white paper. I did not steal it from the Databricks GitHub. So we have our result here being the square root of our input data, and we could just knock off for lunch, but there is more that we could do here. Again, why would we bother doing this function on null data? So let's put in a condition that our data has to be not null. But why would we check each individual value if we knew that all of our rows were inactive? And that's the crux of it. What we're looking at here is still a fragment and won't actually run, so let's build it out. We need to name that function. Let's call it square root kernel. We're going to have to map our specialized functions to our generic ones. No, I don't really know what that means either. We also have to say where our data is going to start, and this is pos list, which is not the data itself, it's just where it actually starts. We also have to say how long it is or how much space it takes up with num rows. And finally, the input of our data is our actual data along with the nulls that we store with it. We also need to pass something out again, and that's going to be our result, and that's going to be defined up front. And then some more brackets. But congratulations, you now know how a kernel works in Photon. Give yourselves a round of applause. This is hard. And not only can these kernels specialize, you can get creative in how to optimize them. Now, at Databricks, we have a pretty good understanding of what gets used a lot. And I would put money on most people in the audience having used a between statement, where we assess one value against multiple criteria. Because we know this is common, instead of going through one kernel for the 2 and then another kernel for the 5, we can just build a kernel that uses a double ampersand in C++. Remember how I said earlier that some characters need less space than others? Well, some kernels are going to detect if all of these characters in the batch are all ASCII characters, like in batch 1. If we can use ASCII, it is much smaller, it is much more lightweight, and it is going to be processed significantly faster. However, if it's not ASCII, it can stick to that heavier classic UTF-8 option, which unfortunately, my friends, means that your Arabic Nando's data is going to take a lot longer to process than your English Nando's data. Another interesting quirk of ASCII is that you only need to switch one number for it to invert the case. So if you had a function like upper, to return everything in all caps, don't waste time checking this value. Just blindly set it to 1 and be done with it. And the last one I wanted to mention, which was UUIDs, universally unique identifiers. These are special kinds of numbers that, to the uninitiated, they look like strings, but if you treat them as the hexadecimal numbers that they take up about half the space. But it turns out, although this was in the white paper, it never made it into production, so sorry. Now, this is just a tiny subsection of kernel specializations. I talk through these ones because I understood them. And whilst all performance are appreciated, these are some of the best, actually. And there is one final one that I'm going to talk through, which is probably going to have the biggest impact on our pipelines, so it is worth our time. And it's the type of query where we play hunt the data value across our workers, and our searching algorithms become really important here. This is the most important for joining, merging, and aggregations across tables, which is 1, everywhere, and 2, it is often the biggest step in a pipeline. Now, a common method original Spark uses is the sort merge join, where we take our 2 tables we want to join, we sort the records in both of them by the join key, and then we merge them, pretty much what it says in the name. But another way to join data is the hash join. Now, instead of sorting both tables, we're only going to sort our smaller table, and we're going to be smart about it. Instead of doing it alphabetically, we're going to take the hash of these values. A hash function is basically a sausage machine. We get the same ingredients, and it always makes the same kind of sausage. And we can see here the blue always gives the same result as 1F46, blah, 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 blah. So what's so great about a hash value? They're more computer-friendly and more efficient to search over than text. You know how we made our UUIDs shorter by treating them as numbers instead of strings? It's kind of like that. We're not looking for green. We're going to look for C862, blah, 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 blah. So with our smallest table, we hash these values. We store them in memory in sensible shuffle partitions and then use this as a lookup table. This means we don't have to expensively sort our second larger table. We can just take the hash value. And now we can search for it in our memory lookup table, making it way more efficient. Now, Spark has been able to do some hash joins for quite some time now, but the benefit with Photon, however, is twofold. One, the actual hash itself is faster, meaning that we have a super speedy sausage machine. And two, instead of doing these lookups one at a time, we can now do it in much faster batches. And for both of these, just like our other kernels, we can upfront ignore rows that we don't need, either because they're null or they're just not relevant to the query. Because of all of this, the Catalyst Optimizer is much more likely to select a Photon hash join than any other traditional join that you might find in Spark. And for most people, this is going to be the biggest performance improvement that you see with Photon. Now, the eagle-eyed of you might be thinking, hey, but what if my data is too big to fit in memory? Photon does intelligently release memory rather than letting it all spill to disk, but that is an entire talk in itself. Now, I'm 35 minutes into query execution engines, and I know what you're all thinking right now. Lebanon delayed daylight savings this year, and that library doesn't ship with C++. Great minds, eh? OK, so it is true. Java and C++ come with different versions of different libraries. And if you're not careful, this can lead to consistency issues. This would be disastrous if suddenly a setting in the cluster changes the output of the data you're seeing. And there's a few tests we can do to check out for this behavior. So the first one is unit tests, where we take our syntax, we're checking its homework by passing it specific inputs, and then checking the output is correct. This is slightly different from Spark's open source unit testing, but don't worry, it integrates with that too. We also have end-to-end tests. This is more testing the behavior if there's an out-of-memory issue. Does it fail in the way that we want it to? And finally, a fuzz test. This is taking random queries with random data, throwing it at both Spark and Photon to see if the output is the same, which I'll be honest, sounds like my normal development style. But what makes this fuzzy? Well, by definition, some of these things are going to be slightly different. For example, Spark reviews the final output types and says, I will process my entire pipeline using this format. Whereas Photon will say, actually, no, that's really dumb. I'm going to do it in a much smarter, faster way. And so, surprise, surprise, you will have some infinitesimally small differences in behavior. When we encounter something like this, we whitelist it. And this technique has the delightful description of a surgical fuzzer. So this has been a whole lot of theory. Let's talk some practicalities. What does this mean for the average Databricks user? Good news, not much. The integration with Spark is pretty slick. By the way, if you ever want to make your account team squirm, ask them, so is Photon actually just Spark? And watch them wriggle as they try to explain all of this in a few pithy sentences. We're still using the same syntax as before, but for anything new, you might want to check that the docs for which functions are included. You can still use the Spark UI in the same way that you would to optimize your code, and the Catalyst Optimizer is still your best friend for making the right choices. With each runtime update, there is more and more coverage, and it's staggeringly fast with what the team is producing. And finally, we've talked about the contents of the Photon whitepaper, which was released over a year ago. There are other enhancements that I've not mentioned at all, which are all having dramatic impacts to performance. Congratulations, you have made it to the end. If I lost you halfway through or even right to the beginning, here are the most important points. 1, enable it at a cluster level with this button here. 2, start using it on your workloads that are heavy on these types of functions. And 3, sit back and enjoy your easy optimization. All right, thank you for being here. You now know more about Photon than the average Databricks employee. If you have questions about any of the things I have said, you can find me, Holly, at Databricks. If you have remaining questions about Photon, for the love of God, don't email me. Email the experts instead. Special thank you to everyone helped with this talk. It has definitely been a labor of love. I'm Holly Smith, and thank you for joining me. You've been a wonderful audience.